Okay, so we're going to look at a new chapter, and that's with chapter 8 with like some applications of triangles. And so what I want to start off with is the law of sines. And it says solving oblique triangles. And really what an oblique triangle means is it's not a right triangle, not a right angle. So, if it were a right angle, it'd be really easy to solve for missing pieces by just using the Pythagorean theorem. But what happens if you don't have a right angle? Then what do you do? So one of the ways to solve this oblique triangle is what's called the law of sines. And the law of sines works. I mean, it's pretty actually easy to prove. I'm just going to draw just an arbitrary acute triangle up here, and I'm going to call this like angle alpha, and opposite it, I'm going to call it side A. And it doesn't really matter like where you put alpha, but A in this context of the section, A will always be opposite alpha. And then beta, which is a Greek letter, opposite beta, that angle I'm going to call side length B. And then side length C, so opposite C, I'm going to call gamma. So you have your angles, alpha, beta, gamma. And again, those are just sort of the default variable for trig when you're doing these. And so what I can actually do to prove the law of sines, again, you don't ever have to recreate this, but, I think it's worth kind of seeing here, where does it come from? If I drop this altitude down here and create a right angle, and then what I'm going to do is I'm going to focus just on, I'm going to focus just on this triangle right here, this blue one, okay? And in that triangle, that red segment that I've drawn there, you can call that like perhaps the height. I need to go to pen, that's why. That's it, okay? Call that the height, okay? And in that blue triangle, I know that the sine of alpha is equal to height over c, because I created a right triangle in there. And so then if I solve for what that height is, whatever side length C is times the sine of alpha, that equals my height. And I'm going to do something really similar in the other triangle that's sitting there. It's white right now. I'll make it green. Like this triangle right here, I'm going to do a sine ratio as well in that green triangle. So if I do that, go to my pen here, I could say, okay, the sine of gamma is equal to h over a, and that's just in the green triangle. And then move that over, a sine of gamma equals h. So I have two expressions that equal h. So I'm going to set them equal to each other. And I got these extra little, getting used to rewriting with my stylus again, sorry. Erase. There we go. Sorry about that. Okay, so back to the pen. There we go. Pen. Okay, so since these are both equal to h, I'm going to set them equal to each other. C sine of alpha equals a sine of gamma. And then what I'm going to do is I'm going to divide this c, divide both sides by c. So I know that sine of alpha is equal to a times sine of gamma over c. And then let's just divide this a across. Divide both sides by a. So sine of alpha over a is equal to sine of gamma over c. And that's actually 2/3 of the law of sines. The other piece of law of sines says that ratio is also equal to, I could have divided it again, sine of beta over b. In other words, in any triangle, the sine of the angle divided by its opposite side. So the sine of alpha A divided by its opposite side, whatever that ratio is constant. It's the same ratio for every set of angles. And so if you know 3 pieces of your 6, and when I'm saying 3 pieces, like there are 3 sides and 3 angles, you can sometimes find the missing pieces if you can set up and solve this ratio. Now, notice I said sometimes. Depending on what you're given, you might not be able to use this ratio. If all you know are the side lengths, right? Like if all you were given are side, 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 like all three sides, you can't actually set up a ratio. You would need law of cosines, which we'll see in the next video. Or if you're given all three angles, then you can't use this either. And so there are some situations that you can use law of sines. And actually, I might as well just tell you what they are right now. Oops, erase. My bad. Okay, so if you have one of the following situations, green. Yep, might as well go green. Okay, so if you're given angle, side, angle, yes, you can use law of sines. You'd be able to set up that ratio and solve it. If you're given angle, angle, side, which is really very similar to angle, side, angle, but it's a different order, and we'll talk about that. You could use law of sines. If you are given, I have to be careful how I spell this, side, side, angle. You can also use law of sines, but this is what we're going to call the ambiguous case. And so I'm going to put a little asterisk by that one, and that's going to come up in this video, I'm sure of it. Okay, so that's called the ambiguous case. And the reason it's called an ambiguous case is because it involves using an inverse trig function, and you're introducing the inverse trig function, and therefore you have to consider both possible angles that could give you that particular value. And so we'll take a look at that. But if you're given angle, side, angle, if you're given angle, angle, side, you can use law of cosines freely without having to worry about any kind of ambiguous case. Okay, so let's take a look at this first example. It says solve the triangle given beta is 34, gamma is 64, and A is 5.3. And remember, we're going to keep this ratio, or this relationship, I should say, that alpha, even if I never put alpha in this left corner, if I put it over here, like if I drew alpha over here, it doesn't really matter as long as I make A opposite it. And if I put beta up here, great, then B is opposite it. If I put gamma here, then C is opposite there. So it doesn't really matter the orientation of your triangle whatsoever. So let's get that guy out of here. Oops, sorry, erase. So let's draw this. Beta is 34 degrees. So we'll go ahead and just draw just a generic triangle. Doesn't have to be drawn to scale. So let's call this 34 degrees. So opposite is going to be side length B. Let's call this 64 degrees. So opposite that's going to automatically be C, which means this is A, which is 5.3, and opposite that would be alpha. Oops, oh, there it is. Okay, so I'm given three pieces, and it says solve. I need to find the other three. Well, the easiest is going to be alpha, because you know, in at least in the Euclidean geometry, the triangle has to add up to 180. So I could do 180 minus 64 minus 34 to get my missing angle of alpha. So alpha would equal 180 minus, I don't know what this little marking is here. Can I erase it? Yep. 180 minus 64 minus 34. So I know that alpha is equal to 82 degrees. So that's nice. Okay. Now, I need to find B and C, and that's where the law of sines is going to come in. If I take a look at what I'm given, like the order of it, notice I'm given an angle, and then a side, and then an angle consecutively. Well, that fits this one right here. Angle, side, angle. So I know I can use the law of sines. So I'm going to set up a ratio. Go a little bit thinner here. There we go. So I'm going to say, okay, the sine of, well, I just found alpha to be 82, and I know it's opposite sides, so that's going to be important. Oops. So sine of 82 degrees divided by 5.3 is equal to, and I could pick either one, maybe I'll do 64 first, sine of 64 degrees divided by C. And so I'm going to cross multiply and solve for C. So now you can't see me doing it on the calculation, but you'll probably hear the click. So I'm going to do 5, and make sure you are in degree mode. So 5.3 times the sine of 64. And then divide by sine of 82. And I'm going to try to go 3 decimal places, 4.810. Okay. And then I have one more I have to solve for. I need to figure out what length B is. So I'm going to do a very similar ratio. Like I'll say maybe sine of 82 degrees over 5.3 is equal to sine of 34 degrees divided by B. And again, you won't see like my calculation, but I'm just clicking away here. You should do the calculation too, just to make sure that you are getting the same answers that I am. And obviously, there's always a chance that I will make a mistake. Oops, like I just did. Let's try one more time. 5.3 times sine of 34. And then I need to divide by, I forgot to divide by sine of 82. So then I got B to be almost 3, 2.993. Okay, so now I have solved for the triangle. I have found the 3 missing pieces. Okay. Let's do another example here. We'll take a look here. It's giving us beta and a B and a C. So it's an angle and 2 sides. So I have to be sort of careful because if this angle and 2 sides, if it forms like a side-side angle, there's a possibility that in this ambiguous case, there might be 0 triangles, 1 triangle, or 2 triangles. So we're going to take a look at that. So let's see. Always got to be careful if it's side-side angle. So beta is 56.3. So I'm going to put that right here. That means opposite it is 8.3. 7.6 I'll put here, which means gamma is up here. Sorry. And that means alpha is here, and this is A. So let's take a look at that order. I'm given an angle, and then a side, and a side. Or if I spelled it the other way, side-side angle. So when you're in a side-side angle case, look out. That's an ambiguous case, and you'll see why. It's ambiguous because you're going to need to introduce the inverse sine function. And when you introduce the inverse sine function, remember, if you're introducing it, introduce inverse sine, that means you need to consider all the solutions or all the roots, and that there are 2 if it's positive, 2 if it's negative. So again, I'm kind of like leading us on here, and it might seem a little like, wait, what's Mr. Brown talking about? But you'll see in a second. So let's set up a ratio. Let's see, I'm forced to use this, this angle and this side. So sine of 56.3 divided by 8.3 as a ratio is equal to sine of gamma over 7.6. Okay, now when I cross multiply, I'm going to get 7.6 sine of 56.3 is equal to 8.3 times sine of gamma. And then divide by this 8.3, notice that you're not getting gamma, you're getting sine of gamma. So I'm going to have to introduce the inverse sine function. So inverse sine of 7.6 sine of 56.3 over 8.3. That's going to be gamma. But since I'm introducing the inverse sine function, so let's do 7.6 times sine of 56.3 divided by 8.3, and I do inverse sine of that ratio. My calculator is going to tell me the angle is 49.6. Oh my goodness. I just can't write. Let's try that one more time. 49.622 degrees. But the thing is, that's not the only angle that would have that particular ratio. Because remember my ratio, before I did this inverse sine, I had a ratio. If you checked your calculator, it would have said like the sine, the sine of gamma is equal to like 0.7617 something, right? And the thing is that in the unit circle, sine is positive in quadrant 1, but it's also positive in quadrant 2. So I could come up with another angle that has this exact same ratio over here in quadrant 2. And so if this 49-degree angle is its reference angle, then the one that would have fit that would have been the supplement to that, right? The obtuse angle. So there's another angle that has that sine ratio. So if I do 180 minus 49.622, I could have had a 130.378 degree angle. And I don't know which one it is. I have to assume there's both until I reach a contradiction. And so that's what makes this law of sines, when you're in a side-side angle case, like I have to assume, oh, I've got two possible angles. I have two possible triangles that could fit this, unless one of them contradicts something that was given. And so I'm going to solve as if both of those angles would work until I reach a contradiction. And so this is what gamma is. And so now I'm kind of already maybe anticipating this contradiction. I already know one of my angles is 56.3 degrees, and one of my gammas was 49.622. So to get alpha, I could do 180 minus 56.3 minus 49.622. And if I do that, let's see, 56.3 minus 49.622, I get 74.078. No contradiction there. So that could be my first alpha. But then in the second triangle, like if I think about alpha 2, I still know they add up to 180. I had originally a 56.3, and I also could have had a 130.378. And if I subtract those, I don't even need to do this, but just because of my OCD, I will. I'm going to get a negative answer, 30.378. And what that just means is that even though I had two possible angles for gamma, I can't have two possible angles for alpha. There's a contradiction. So now I know there's only one possible triangle, not two. Sometimes when I solve for the second one, and that's what the next video is going to show a couple more examples of, sometimes when I solve for the second one, it's still going to fit that triangle. And so I'm going to have two different triangle solutions. But for now, I just have one triangle. So I found my alpha, I found my gamma, and the only thing I'm missing now is length A. So then when I find side A, let's erase this over here. Erase this. So let's actually go ahead and set up our ratio to solve for A. So sine of alpha, which we just got, was 74.078 divided by A is equal to, and I'll just stick with the sine of 56.3 divided by 8.3. And so we cross multiply. Notice like when I'm solving for alpha here, right? No ambiguity. No, I'm not introducing anything. So it's just going to be what the calculator says. 8.3 sine 74.078 divided by sine of 56.3. Okay, so I got A to be 9.594. Now, if you're off by like a thousandth of a decimal, that's okay. I'm trying to round to that third decimal place to give as much accuracy as possible. So there I've solved for the missing pieces. And I know I kind of solved all over the place. So if you wanted to kind of maybe put them all together, somehow say, okay, so I found A to be 9.594. I found alpha to be 74.078. And then I knew that gamma was equal to 49.622. Okay, that's our first taste of the law of sines when we're in this situation, the side-side angle. And that's what the next examples are going to show as well. Sometimes, like I said, you might get two triangles. This angle here might be small enough when you solve for it that it still fits with the given angle, and you could still create a second triangle. Okay, so I'm going to switch out a new video, and then we'll just keep doing some more examples and keep going from there.